Welcome to MAT 1510, Deep Learning Theory and Data Science. I received an email which says that students have told us that direct encouragement from their instructors is one of the most important factors influencing their decision to fill out their course evaluations. So I thought to myself, this is me showing direct encouragement for you to fill out the course evaluation. If you want to complain about, me having strange pronunciation of certain words, this is the time, or any other issues you might have with the course. So previously, yeah, previously, that's not my fault. Previously, we discussed about the neural tangent kernel. I wanted to start with a small reminder of what that is. Just a very short reminder. So, what is happening with this screen? 1 second. Okay, so the neural tangent kernel, which is the NTK, we saw that it's just defined as theta xx, and it's defined to be this matrix. The derivative of the logits with respect to the parameters times the derivative of the logits with respect to the parameters transpose. That was the definition of the neural tangent kernel. And we spoke about how the neural tangent kernel converges at initialization as the width of all the layers tends to infinity to a fixed limit. That was the first theorem we discussed. And the second theorem we discussed was that the neural tangent kernel is fixed as we train the network. And then we discussed the implications of these theorems. The first implication was that if the neural tangent kernel is fixed, it means that the dynamics of the logits f are described by a simple linear differential function, where here you can see the logits f, here you can see the logits f, and here you have a fixed NTK matrix. And we saw that we have a solution, of course, to this linear differential equation that you might have seen in a differential equations course in your undergraduate studies. And the second thing we saw is that there is a different perspective on the NTK besides the linear differential equation on the logits. You can also think of this as implying that the model can be linearized into some f bar, and then we can look at the loss of this linearized model and look at the dynamics of the linearized models and so forth. And so basically what you see if you do that is that the NTK is essentially saying that your landscape is equivalent to some type of a quadratic ball. Quadratic balls look like this, where this quadratic ball can be characterized using the NTK matrix. So it's kind of like a simple quadratic optimization problem. And we remember that Tristan had some issues with all of these statements, and I think a general lack of belief in what was being said. Is that correct characterization of your response last week, Tristan?
A little, yeah. I was intrigued is a positive way to.
Okay, intrigued is good. And okay, so you also had a homework that you might have started or have completed, where in the homework, what you're doing is looking at the spectrum of the Fisher information, which is equivalent to the spectrum of the NTK. And the homework should ideally show that the spectrum of the Fisher information matrix / NTK converges to some fixed limit as the width increases. So what you should see in the homework is, so here you have lambda, here you have the probability of lambda or the count of lambda, however you want to think about it. And if you look at a certain width, you see something, something. And then if you look at a larger width, you see something, maybe something a bit different. And then if you increase the width, eventually you should see that you converge basically to a fixed limit, right? Has anyone achieved such a fixed limit in their homework? No. RAM issues. Okay, so unfortunately, there is no empirical evidence thus far. And okay, sort of. What does it mean, sort of, Karen? There is convergence of some kind. Okay. Kind of. Okay. Okay. Kind of. So does anyone have any questions about the NTK summary, the very brief NTK summary, before we proceed?
I've got a quick question. If you go back to the one about the convergence in training, like it was uniform convergence over a time interval 0 to t. Yes, this one. So since it's uniform in the training, does it really mean that it works for any values of the weight matrices?
So the assumption here is that you initialize the weight matrices as a Gaussian with a certain variance, right?
And then even as you train, like I'm just thinking that arbitrary things could happen as you train. So does the thing really hold for any arrangement of weight matrices?
They seem to claim yes.
Huh.
But there is a caveat, there is a twist in the plot, as we mentioned last time. Today we shall see the twist in the plot. Buckle up. So let us see the tweet. This one. Right, so in today's lecture, we're going to discuss something called lazy versus active training. Lazy versus active training. So the idea is as follows. In our course, we've discussed the concept of max margin classifiers. We've discussed, so max margin classifiers, I remind you, are classifiers where you have some data here, you have some data here, and you're trying to find a classifier that separates the data perfectly, but somehow maximizes the margin, right? We've seen the concept of neural collapse. Neural collapse is a phenomenon where essentially all the training points converge to a certain point, and you get a simplex ETF structure in terms of the classifiers, the class means, and the within class covariance converges to 0. And now we've seen this neural tangent kernel, which seems to indicate that the optimization of deep nets is somehow equivalent to a quadratic ball. And we should have seen a lecture on sparsity, but it seems like maybe we'll see it next week. And the question is, how can we relate all of these topics together to get some type of a global picture of what's happening in deep learning, of our understanding of deep learning thus far? So that's what we're going to try and do today. So the paper I'm going to discuss is called On Lazy Training in Differentiable Programming by Shiza, Oyalon, and Bach. And the abstract goes as follows. In a series of recent theoretical works, it was shown that strongly overparameterized neural networks. So notice when they say strongly overparameterized neural networks, they mean basically very wide networks. Trained with gradient-based methods could converge exponentially fast to zero training loss with their parameters hardly varying. So when they say parameters hardly varying, what they mean is that in this NTK regime, it was observed that the parameters actually don't change too much. They vary by a little bit. In this work, we show that these lazy training, so they use pejorative, words to insult NTK. This lazy training phenomenon is not specific to over-parameterized neural network and is due to a choice of scaling. Let us highlight this with an important color, the red color, is due to a choice of scaling, often implicit, that makes the model behave as its linearization around the origin, thus yielding a model equivalent to learning with positive definite kernels. So hopefully the words positive definite kernels mean something to you at this point. Through a theoretical analysis, we exhibit various situations where this phenomenon arises in non-convex optimization, and we provide bounds on the distance between the lazy, again they use pejorative words, and linearized optimization paths. Our numerical experiments bring a critical note as we observe that the performance of commonly used nonlinear deep convolutional neural networks in computer vision degrades when trained in the lazy regime. This makes it unlikely that lazy training is behind the many successes of neural networks in high dimensional tasks which are difficult. So first of all, I would like you to appreciate the fact that you likely understand most of this abstract, right? You can see how much you've come throughout this course to the point where you read an abstract which was written by researchers maybe a couple of years ago, maybe 1 year ago, and you actually understand most of the words written here, which is cool, right? And so what is this abstract? What is this paper actually saying? So the paper says the following. The paper says, imagine you look at the optimization problem of a deep network. This is the optimization problem. We have the loss, we have the logits F, we have the training data X, we have the parameters of the model theta, and we have the labels Y, right? This is the training of a deep network. Now imagine that we take the nonlinear model here. This is a nonlinear deep network, and we just linearize it. So how do you linearize it? Using what? How do people linearize things in life?
It's using the Jacobian?
Yeah, so basically, yeah, exactly. Jacobian and using the Taylor series. And so here's a quote from the paper by this author. So the quote says, "It is a general fact that the optimization paths, the original one and the linearized model one, are close at the beginning of training," right? That's kind of hard to disagree with. We call lazy training, again with these pejorative words, the less expected situation where these two paths remain close until the algorithm is stopped. So they're saying that lazy training is the less expected situation where Taylor approximation keeps holding for the whole training, right? Now, what they're trying to do in this paper is explain why are we in this lazy training regime? Why? So they begin by showing a nice illustration. So what is this illustration showing to you? Let's begin with a simple high-level explanation of what this illustration is showing us. So on the left, you can see, first of all, that there's 3 vectors. Do you see 3 vectors in this space? Think of these 3 vectors as 3 directions which are associated with a certain prediction function. So let me write this down. So let's define f of, let's say, x and parameters w to be equal to sum from j equal to 1 to m, a j max, I guess I could just write here ReLU of b multiplied by x. Okay, so what is this function? This is a function. Okay, maybe someone should answer the question. What is this function in your opinion? If you had to describe it succinctly, I don't know that word. Succinctly. How do you pronounce that? Succinctly. There's no way I'm pronouncing that correctly.
Succinctly?
Yeah, that thing. Yeah, thank you. So what is this function? What is this function trying to tell you?
It's just a 2-layer ReLU neural network.
Yeah, exactly. So this is a 2-layer ReLU neural network where essentially this thing is the first fully connected layer that multiplies the input x by a certain scalar in this case. Then you apply a ReLU, then you multiply by a j, right? I guess we could draw this neural network just to, let's see. Let's draw this neural network. You know, in deep learning, it's important to draw. Otherwise, it's hard to understand. So here's the neural network. Here you have x. Here you have the weights aj. Here you have the other weights. And here you have the output f of x, w. And somewhere in between, you have the ReLU non-linearity. Make sense? Now, imagine that we have an underlying truth given to us by God. So God created a small neural network where m was equal to 3, right? And for that m equal to 3, we have a1, b1, a2, b2, a3, b3. And imagine that for some reason, aj times bj is equal to 1. So it's like normalized, okay? Then in such a case, you can think of these 3 aj, comma bj as just 3 vectors, right? 3 vectors. So these are these 3 vectors. It's basically the 3 true directions that are required in order to predict some data. And imagine that we generate data using this small architecture with m equal to 3. And we generate basically the labels, which are the f's. And then we take all of this data and we train a large network with a large M on that. Does that make sense? So in the, I guess in the physics community, they like calling this a teacher-student experiment or network. So who is the teacher here? The teacher is the God-given architecture, which has 3 directions. So A1, B1, A2, B2, A3, B3. And the student is the larger architecture that's trying to learn the function that the smaller network is inducing. Does that make sense? So in the ultimate truth is these 3 directions that you have here. And what we do is we train a neural network that has more neurons. How many neurons does it have? As many as the different dots you can see here, right? And what this plot shows to you, so let's just count. It's like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12 different neurons in this case. Now, what is this plot trying to communicate to you? This plot is showing you tau equal to 0.1 and tau equal to 2. So let's read the description of the caption of the figure. It says, training a 2-layer ReLU neural network, so that's what we've been talking about now, initialized with normal random weights of variance tau squared. Let's highlight this very important statement. Variance tau squared, random weights variance tau squared. Lazy training occurs when tau is large. So if tau is large, you can see that the trajectory of the weights is very small. So the weights are barely changing. So if you zoom in, this point is the point of initialization and it's moving only a bit, right? Do you see how small the trajectory is? Basically, no movement. On the other hand, here you can see how the trajectory is very large, right? So what do you learn from this plot, or from this experiment rather? You learn from this experiment that if you initialize your network with a large variance, if your weights are initialized with a large variance, then you're going to enter the lazy training regime where your weights are going to barely change. On the other hand, if you initialize your weights with a very small variance, then you're going to enter a non-lazy training regime, active regime, where your weights change significantly. And you can also see that, notice how all the weights, all the neurons are converging to these three ground truth God created directions. Neo is asking, but aren't the two pictures scaled differently? I'm not sure what that means. Aren't they scaled differently? No matter, sorry, go ahead.
I mean, like you said in the second picture, things are not moving as much, but then in the first one, the circle is bigger. So I wasn't sure if it's that convincing pictorial.
But no matter how, let's just extend this. I understand what you're saying, but let's just extend, right? Here's an extension. Do you agree that there is no movement in the lazy training, right?
Oh, I see. Oh, I see. I was confused for a moment in terms of, I thought you have to shrink the circle to make it. I thought the data are scaled differently in two pictures.
No.
Okay, sounds good. Thank you.
Jack is saying, is all of this happening in the teacher model? So let us ask the rest of the students. Do you think this is in the teacher model or in the student model? Tristan is nodding negatively. In some cultures, this means actually yes. So it's not the...
Yeah, I think it's happening in the student. The teacher's not trained.
Yes, that is correct. Thank you, Tristan. So indeed, the teacher is not being trained. The teacher has been granted to us from God three directions, which are the ultimate truth. Whereas the student is trying to get close to God's directions. And so you can see here the student. So one indication that this is a student is that the neurons are changing. Another indication is that the number of neurons is greater than 3. The student does still have 2 layers. That is correct. Yes. So let me just emphasize again, that the teacher has this AJ, BJ from J equal to 1 to 3. And these are normalized to unit length. That's why essentially what's happening here is that this can be thought of as AJ, and maybe this is BJ. I don't know if this is what, if this is AJ, this is BJ. It might be the opposite, but you get the point, I think. Okay, so on the right-hand side, you can see the generalization properties. So you can see the this curve shows the test loss as function of tau. So here we're lazy and here we're active, right? Like these words. So in the active regime, your test loss is very small. In the lazy regime, your error is very large. Okay. Now, what is this slide telling you? This slide is telling you that if you change your initialization, then you might enter the lazy regime or the active regime, but it does not explain why, right? It does not explain why. So the next part would be to explain why or when. When does lazy training occur and why does it occur? So consider the following important quantities. What we're going to look at is the relative change in loss versus the relative change in Jacobian. What do these words even mean? So first of all, notice that if you have a system which undergoes gradient flow optimization, then you can actually calculate what is the change in loss with respect to time. So this quantity is just basically saying by how much is the loss changing at each point in time, right? Now, using our beloved theorem, which goes by the name of chain rule, we know that the derivative of the loss with respect to time is the derivative of the loss with respect to the parameters times the derivative of the parameters with respect to time, right? Why are we calculating here an inner product between the two? Because we're expecting to get here a scalar, right? The derivative of a scalar loss with respect to scalar time is a scalar. I guess it's a horrible reason for why you would calculate the inner product, but I guess what I'm saying is that at least the dimensions make sense, right? Now, notice that we actually know what is the gradient of the loss with respect to time. Does anyone know what is the gradient of the loss with respect to time? Let's sip my tea. Homework 1. Homework 1.
Sorry, you said the gradient of the loss with respect to time?
I meant the gradient of the loss with respect to the parameters. I'm sorry. So basically this quantity, what is this quantity? If you look at the gradient, no, it's not the Haitian. Okay, this thing is just the gradient, right? This is the gradient of the loss with respect to the parameters of the model. So this is literally the gradient that is being used by, by optimization of SGD, right? It's just a simple gradient. What is this quantity? What is this quantity? What is the derivative of the model parameters with respect to time?
It's just the negative of the gradient.
Yeah, exactly. Thank you. Thank you. So it's just the negative of the gradient. So it's minus gradient theta of the loss, right? So notice that we have the gradient of the loss here. And we have the gradient of the loss here. So it's just minus the L2 norm squared of the gradient of the loss with respect to the parameters, right? So you get a very simple expression for how is the loss changing with time. It's just minus the norm of the gradient, L2 norm squared, right? Now imagine that we're interested not in the change in the loss. This quantity is kind of meaningless because the change in the loss is not very it's not a good quantity to look at. A much more reasonable quantity to look at is the change in the loss divided by the loss, because then you get a relative change in loss. Usually in life, you should always be looking at everything relatively, right? Looking at quantities absolutely is a bad idea, since you don't know where the minimum is. It's just because you want to look at the change in the loss, but you want to normalize the change with respect to how large the loss is. Like if I tell you that the change in the loss is 0.1, what does that tell you? Nothing, right? If your loss is 100 and your change is 0.1, then the change is meaningless. But if your loss is 0.2 and you have a change in the loss of 0.1, then it's significantly more significant change, right? So that's why we're looking at the change of the loss normalized by the loss, and we add a minus because we hate minus signs, right? And so we get this very simple quantity, The other thing that we're going to look at is the change in the Jacobian. But why? Why would we look at the change in the Jacobian? Why do we care about the change in the Jacobian?
Because it measures the departure from the linearization.
Yeah, exactly. Measures the departure from the linearization. If the Jacobian is fixed, it means that we're always in this linearized lazy regime, right? And so what is the change in the Jacobian? So it's basically the derivative with respect to time of the Jacobian, right? And so how does one calculate the derivative with respect to time of the Jacobian? Which theorem are we going to use? The same theorem that we always use, the chain rule. So what is the derivative with respect to time of df to d theta? It's the derivative of df to d theta with respect to theta times the derivative of theta with respect to time, right? And so the derivative of f with respect to theta usually goes by the name of a second derivative. So we get a second derivative of f with respect to theta times the derivative of theta with respect to time. But what do we know about the derivative of theta with respect to time? According to Jim, Shaw, and Neo, it's just equal to minus the gradient of the loss with respect to the parameters, right? So we got this expression. Now, again, looking at changes of Jacobians is not a good idea. Why? Because we must always look at everything in a relative manner. So in this case, we need to look at this change in Jacobian also relative to something, right? Now, notice that this change in Jacobian, what is this thing? What is this? What is this?
Is it a matrix vector product?
It is a matrix vector product because for today's lecture, we're always assuming that f is a scalar for simplicity. Otherwise, things get a bit annoying. And so if f is a scalar and theta is a vector, then the second derivative of a scalar with respect to a vector gives us a matrix, right? And the gradient of the loss with respect to the parameters is a vector. So this thing gives us a vector, right? So if we want to quantify its magnitude, it's going to be through an L2 norm of a vector, right? But we want to look at this relative to the magnitude of the Jacobian, right? How does one measure magnitude of a Jacobian? Frobenius norm is one option.
You could use the operator norm.
Operator is the second option. That is correct. So in this specific case, we're going to use the operator norm. And so basically the operator norm is just the maximal singular value of the matrix. Those of you who like singular values, which seems like not many of you, unfortunately. Now, what we're going to do is we're going to take this quantity, and which is the change in the Jacobian, and normalize it by the norm of the Jacobian. And we're going to use here a property, which is the, does anyone know which property this is? How are we bounding this through this? Any experts in linear I don't know, this is taught in linear algebra. Linear algebra 2, 3, 4. I know which course.
It's just the definition of the operator norm, right?
It's just the definition of the operator. Yes, that is correct. Because the operator norm is just the maximal magnification of the L2 norm of a vector after you multiply by a matrix, right? You can also think of it as a multiplicative norm of the induced norm. But basically, we got this expression which reflects the relative change in the Jacobian, right? And so what the authors of the paper propose is that lazy training, again with the pejorative word, occurs when the change in the loss is significantly larger than the change in the Jacobian. So if you manage to significantly decrease the loss without changing the Jacobian, then you're being lazy. How is that related to variance? Asked Jack. And we shall answer Jack's question in the next few slides. So to summarize, what does greater precisely mean? It means that it's significantly larger. You don't like this. Significantly larger is okay. We'll also answer your question. Yeah, we'll hopefully make it a bit more, ever so slightly more precise, ever so slightly. So to summarize, what's the meaning of relative change of Jacobian? Deviation from linearization, asks Samireza. The answer is yes. So if the Jacobian is changing significantly, it means that the Jacobian is changing. So it means that you're, it just means it's actually not really deviation from linearization. It's more like deviation from the linearization at initialization. How does it relate to lazy training? So lazy training is the phenomenon that's basically NTK. So it's a phenomenon where your optimization is optimizing essentially a quadratic function defined through the Jacobian, df to d theta. And so essentially lazy training is equivalent to saying NTK regime, and it's equivalent to saying that your Jacobian is not changing. So you're just optimizing this quadratic ball defined through the Jacobian. Does that answer the question, Mirza? Justin is asking, what is lazy training? Didn't quite get it. Does it mean the learned parameters are not far from starting point? Yes. Here you can see the words lazy training, right? And it shows that lazy training is when the parameters are barely moving. You see, barely moving, they don't change. This should be contrasted with active learning when your parameters are significantly moving, significantly changing. Does that answer the question, Justin? Jack is asking, intuitively, can we think of it like this? If loss changes a lot more than Jacobian, then the loss function can be minimized without moving too much, thus resulting in lazy training. That's precisely correct. That is precisely correct. That is precisely correct. So here again, this equation says relative change in loss significantly greater than relative change in Jacobian. And so what we're going to do next is we are going to discuss how is this related to the variance of initialization. You guys don't seem to like rough. This is like a commonly I mean, what would be a proper definition for you? Like, you want O notation, O of? Greater is, you want delta epsilon, okay, yeah. Big O. Choose whatever definition you like for greater, and just let's assume that's what's meant. This is another case of don't shoot the messenger, don't shoot anyone, but don't blame the messenger. Maybe that's there's some saying that I'm the messenger. I present to you a paper the way it was presented in the original paper, right? So if the original paper did not explain what does greater means, then unfortunately, I can only guess what they mean. Or I don't remember them explaining what is greater, but maybe you can look at the paper and inform. So what we're going to do is we're going to assume that we have a mean squared error loss, because mean squared error is very nice. So here's a mean squared error loss. As a result, the relative change in loss, which we've just discussed in the previous slide, Reza is asking, does the term lazy come from training the network without putting much effort into changing the linearized network? Yes. 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 Lazy because the network remains in this linearized regime. NTK. NTK, lazy. So if you look at the relative change in the loss, you can actually, this is the relative change in the loss. You can actually simplify it a bit by noticing that the derivative of the loss with respect to the parameters using our beloved theorem of chain rule is equal to the derivative of the loss with respect to the logits times the derivative of the logits with respect to the parameters, right? And you can actually, why would you want to do this chain rule? Because then you can actually cancel this thing and this thing, right? So here you have a L2 norm to the power of 2. Here it's just to the power of 1. So you cancel this with this, and you're left with this quantity, right? So it's just simple inequality that leads to a slightly more, slightly simpler quantity. So if we plug this inequality into the previous slide, we get that lazy training occurs when this happens. So in the previous slide, we had the gradient of the loss with respect to the parameters divided by the loss. Now we have this quantity instead. Just some manipulation, simple manipulation. Now you can actually rearrange this into just one having to be greater than this quantity. So it's just basically putting everything on this right-hand side of the inequality. And we're going to denote this whole quantity as kappa of theta. Kappa of theta is what dictates whether we're in a lazy regime or active regime. Okay. Okay, so thus far what we've done was explain hopefully what is lazy versus active training, and explain how to measure this lazy versus active training through this function kappa. But Jack asked us, how is this related to initialization, right? So if you reward Jack's question, Jack is actually asking, how is kappa related to the network initialization variance? Gina has a question.
Sorry, just to clarify, so active training is like the normal training, and then lazy training is just with the linearized version.
Yes.
Okay.
Yes.
Thank you.
Yes, and lazy, the linearized thing is also what you have in the NTK regime, right? In the NTK lecture, we were talking about how in the linearized network, you have essentially the same dynamics as NTK. NTK, lazy, linearized are essentially all synonyms to the same thing. Okay. This expression f times double dot f divided by f dot squared appears many times in physics to describe phase transitions. Okay, so we see it once again in a non-physics context. Okay, so what we're going to do now is we're going to discuss a special family of functions that people like. These are called homogeneous functions. Have people heard about homogeneous functions in their previous lives prior to this course? Luke has had an encounter with them, which seemed not positive based on his reaction. A non-positive encounter with homogeneous functions. So what is a homogeneous function? A homogeneous function is simply a function that satisfies f of alpha theta is equal to alpha to the power of L f of theta. So f is positively homogeneous of degree L if for every alpha greater than 0, this is satisfied. Okay. Now, in simple words, it just means that you can take a constant alpha outside of the function, but you need to apply a power to it. Now, can anyone give me a simple example of a L homogeneous function? What would be a simple example? No. X to the power of L, that is correct. So fx x to the power of L satisfies that f of alpha x is equal to alpha to the power of L f x, right? ReLU is homogeneous, that is correct, but it's not L homogeneous. It's just one homogeneous, right? Yeah, ReLU is a correct answer if you consider one homogeneous. That is correct. F equal to 0 works, right? Yes, it seems like it does work. Yes. Now, what property do homogeneous functions? There is one property that homogeneous functions satisfy that is going to be of utmost use to us. And that property is that if f of theta is a positively homogeneous function of degree L, and if you differentiate it, then you get a function which is positively homogeneous of degree L minus 1. And if you differentiate it again, you get a function which is positively homogeneous of degree L minus 2. Beautiful properties, aren't they? Truly beautiful. Now, why do we care about homogeneous functions? Does anyone know? Have we just drifted into unrelated topics, or is there a single thread, a single thought thread? How do you say that? Thought thread, line of thought, a single line of thought in this lecture. How are homogeneous functions related to us? Maybe you can like normalize things. Might be related to the kappa constant. Yeah. Yes. Yes. So what would be an example of a homogeneous function in deep learning? What is a homogeneous function in deep learning? Neo likes his ReLUs, it seems. Yes, Neo, there is going to be a ReLU. That is correct. That is correct. But okay, let me challenge you, Neo, since you like your ReLUs. What would be an example of an L homogeneous function in deep learning? I too like ReLUs, I must say. What would be an example of an L homogeneous function in deep learning that we definitely care about? Let's put it that way.
Would it be something like the loss as a function of the weights?
Yes.
They all multiply.
Yes. 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 So what reservation? So what Tristan is saying is that the loss function of, as function of the parameters, not quite. There is a pickle there.
I
So-
guess the logits as a function of the.
Yeah, so Tristan is getting warmer. The logits as function of the parameters do seem like a homogeneous function. But what is the problem with Tristan's proposal? What is the problem? The bias, wow. Wow, that is correct, Jack, the bias. The bias prevents us from having a homogeneous function. So imagine that we eliminate all the biases because we want to force this idea, right? That's what you do in science. If your idea doesn't work, you just force it brutally. So imagine that we look at a network that looks like f of x theta. So this is a Tristan's proposal. Look at the logits as function of parameters is equal to W3 times a ReLU of W2 times a ReLU of W1 times an X, right? This is known as a 3-layer fully connected ReLU, because we like our ReLUs network with no biases, because Jack told us that you cannot have a bias, right? Now, why is this function? So first of all, this function is 3 homogeneous. Why is it 3 homogeneous? Because if you insert a constant alpha multiplied by all the parameters, then you're going to have an alpha here, an alpha here, and an alpha here. But you can, of course, gather all of these alphas outside of this expression and get alpha to a power of 3 multiplied by f of x theta. Does this make sense? Now, why can't we have a bias? Because it doesn't work for a bias. You can check for yourself. Okay, so.
But I guess it wouldn't work when we do it to the x, right? If we were to multiply alpha times x. Like what do we do when there's many variables in the function?
Oh, so maybe I should say that we're talking about homogeneity with respect to the parameters, not with respect to x. It would be one homogeneous with respect to x, right? One homogeneous with respect to x. It would not work with a bias. It would not work with a bias. Just try it. Let's try. So there's something called Euler's homogeneous function theorem. Have you heard such a theorem? Very useful. Euler's function homogeneous theorem is literally the only theorem that you need to know about homogeneous functions. The theorem says that if you're, let me just see that I quote it correctly. So the theorem says that if you calculate the derivative of a function f, which is positively homogeneous of degree k with respect to theta, and you do an inner product of this quantity, I guess I should do it like, oops, inner product with theta, then you're going to get L times f of theta. This is Euler's homogeneous function theorem. Why is this correct? I guess you can do simple examples. Let me just show you a very simple example that maybe would explain why you cannot have a bias. Imagine you have f of theta. So you don't want to see my example, Neil? I won't do it if you don't want to do it. I'll do it anyway. So imagine if you have f of x theta equal to something like, you know, a weight times x plus a bias, right? If you calculate the derivative of, if you calculate the derivative of f with respect to theta, you would get just x, and then inner product with w, I guess they're scalars, so it's just w times x, and that's not equal to 1, which is the, in this case, it's 1 homogeneous times wx plus b. So based on Euler's homogeneous theorem, you can show that it's not a homogeneous function.
But wouldn't the bias also be included as a parameter?
Wouldn't the
Yeah, that's what I
bias-
was wondering. But I think I answered my own question, because if you only have one ReLU, that would work, because you can just pull out the alpha from the bias and from the linear matrix, and then you pull it out of the ReLU. But then if you apply bias on the outside again, and then you hit it with another ReLU, it's not gonna work, because then you have an alpha square here, and then you only have alpha on your bias. Like the power on the bias doesn't accumulate, where the bias on the linear one would. That's what I was thinking. Probably that's why it doesn't work. So it only works with if you only have one ReLU.
Yeah, I think I understand what you're saying. Maybe we can discuss this at the end. It's not particularly important. Last time I thought about this deeply, I came to the conclusion it is not, I guess in this case, if you look at the derivative, I guess what you're saying is if you look at the derivative with respect to b as well, right? And you concatenate a 1 to x, it does look like it's one homogeneous. My example has unfortunately failed. Okay, so we're going to focus on the no bias case. We can discuss what happens if you have a bias in the end. How is any of these related to lazy training? So as was suggested in the chat by Jack, we're going to look at the kappa of a L homogeneous network, right? So here's the kappa. Let me highlight the important thing. So here's kappa of alpha theta 0. So what happens if we multiply theta 0 by alpha? It's equivalent to just scaling your initialization by a certain factor, right? Now, what do we expect to see? We expect that if alpha is very large, then we should enter a lazy regime, which would mean that if alpha is very large, kappa should be very small. So by definition of kappa is equal to the thing that's written on the right. Let me just highlight that here I'm plugging the alphas in the different locations necessary. So all the different places where theta 0 appears, there is now alpha theta 0, right? Now, what we're going to do next is use the property that we learned about homogeneous functions. The property says that a homogeneous function, by definition, you can take the alpha outside of the f, right? So you get alpha to the power of L. If you're looking at the second derivative, you get alpha to the power of L minus 2. If you're looking at the first derivative, you get alpha to the L minus 1. Very simple. Now, at this point, what we're going to do is just gather all the alphas together. And once we gather all the alphas together, we can see that we can simplify this alpha expression to 1 over alpha to the L. What does this mean? It means that assuming you believe that this quantity is small or that it's bounded by something, right? Say this is bounded by 5, then if you increase alpha, then your whole quantity is going to decrease. And that means that kappa is going to be smaller and smaller. And that would lead us to enter the lazy regime. So let me just remind you again, alpha large implies kappa small, which implies lazy training. Okay, does this make any sense?
Wait, isn't there still like an alpha L inside the?
Yeah. So the way you resolve that issue is by convincing yourself that this quantity is actually just some bounded quantity. Why would that be the case? You might ask yourself. So if you think about it, then if you look at a two-layer network, for example, notice that you can write a two-layer network as f of x theta equal to sum of AI ReLU times BI times X, right? This is the example we saw earlier. Now, it's quite easy to convince yourself that at initialization, this is obviously positive, right? And the AI has usually a distribution which is symmetric around 0, right? So it's some distribution that's symmetric around 0. So that implies that your AIs are going to be sometimes positive, sometimes negative. And so if you have a sum of things which are sometimes positive, sometimes negative, and everything is symmetric, then you're just going to cancel all of these quantities and be around 0. Does that make sense? Neo seems unsatisfied with my explanations today. So Neo, you shouldn't blame me for this lack of, again, don't shoot the messenger, shoot don't shoot anyone, but if you have to, don't shoot the messenger. I don't think they explain this properly in their paper, but you're free, of course, to read their paper. Maybe you see something that I missed. Okay, so this is one example of homogeneous models that show that one enters the lazy regime with large initialization. But in their paper, the authors proposed a different setting where one can analyze when is the lazy regime happening. Okay. The different setting is related to the title of this lecture. The different setting is the two-layer infinite width case. What is this? So the two-layer infinite width case. So in this case, what we have is a function that looks as follows. F of x theta are the logits are equal to sum over the different neurons in the hidden layer, and the sum is over g of x phi I. And so here's a simpler equation. It's just AI nonlinearity wix plus bi, right? This is, again, a two-layer network, Now, the important thing about this two-layer network is alpha m. What is alpha m, you might ask yourself? Alpha m is a function that depends on m, which is to be specified. Okay. Do you want me to create an illustration? Here's an illustration. So, illustration. This is infinite width network, right? Bunch of nodes in the hidden layer from 1 to m. This is xi. This is wi. This is ai. And this is f of x, and I ran out of space. Okay. Now, the question is, when does this two-layer infinite width model enter the lazy regime? That's the first question. The second question is, if it is not in a lazy regime, where does this model go to with training? Isn't that an interesting question? Where does this model go to with training if it's not being lazy? Now, what they show in the paper is that the expectation of kappa m, which is basically kappa if you have width m, is upper bounded by 1 over square root of m plus 1 over m times alpha m. Okay, so it's a sum of two quantities. Now, notice that as m tends to infinity, there's two interesting cases. The first interesting case is if m alpha m tends to infinity. If m alpha m tends to infinity, then this thing tends to infinity. And this thing tends to infinity just by the fact that your m tends to infinity, right? So if m alpha m tends to infinity, you get lazy training. Now, here's a trivia question that might help some students with their homework. What is alpha m equal to in, let's say, the NTK network that we discussed in the previous lecture? Does anyone know? What is alpha m equal to in that case? Hard question. So let us look at the previous lecture slides. So in the previous lecture slides, I actually skipped a single slide, maybe purposefully. So the slide says the following. Here's a standard network, and here is the NTK network. In the NTK network, the initialization of the parameters is Wij normal 0, 1. And if you look at the paper very closely, they multiply the weight by 1 over NL. So that's equivalent to saying that the weights are initialized as a normal 0, 1 over square root of NL. And so in regular training, usually you initialize your parameters with a variance of 1 over n. So it's 1 over square root of n versus 1 over n. So let us jump here again. Notice that if you have alpha of m equal to 1 over square root of m, then m times alpha of m is going to tend to infinity, and you will be in the lazy training regime. NTK will be in the lazy training regime. However, if you use alpha m equal to 1 over m, then you will get a non-degenerate dynamic, active learning, and this is called the mean field limit. Does anyone know how is this related to the homework? Some people do. Yes. The homework doesn't use NTK. It does do NTK. It's supposed to do NTK. It's supposed to NTK. It's supposed to. You see, there was a malicious person in the homework who might have switched the dynamics from NTK to some wacky dynamics. Is this upper bound tight? I don't think that was discussed in their paper. I don't think that was discussed. So I actually have a slide which roughly explains the derivation. So let me go in high level over the derivation so you don't get flooded with details. Let's use beautiful colors. Okay, so our goal, let us put our goal in red. This is the goal, or this is what we care about. This is the kappa function, right? And we care about characterizing the kappa function, saying something about it. So notice that the kappa function has certain ingredients. The first ingredient is f of x theta, L2 norm, right? The L2 norm of the logits. So the L2 norm of the logits is being calculated in this row. The second quantity of interest is the induced norm of the Jacobian, of the second derivative of the logits with respect to theta. So it's actually a Hessian already. So this quantity is being calculated here in this line. The third quantity of interest, let us highlight it in pink, is the induced norm of the Jacobian, and this quantity is being calculated in this line. Let's say this line. You can actually ignore this, just ignore this quantity. And so roughly speaking, what the argument does is just uses simple bounds, just simple bounds. Let me illustrate this. For example, if you would like to calculate how is the expectation of this quantity behaving. So the expectation of this quantity squared is equal to what? It's just the expectation of the L2 norm squared of the logits. So if you just take this function, calculate L2 norm squared, then you would just get that all the terms in the sum which don't have the same index are independent. So the expectation is 0. And you would simply get a sum of squares, right? Squares of these quantities. And if you get the sum of squares of these quantities, this is why you have expectation of g squared. So just the expectation moves inside the sum, basically. Does this make any sense? It does. And so essentially, because g is some function, you know, pick whatever function you want, the expectation of the function is just some constant. So you can just call it C1. And what's important is that this constant is being multiplied by m and alpha m squared. So that's one of the quantities. Maybe I can show another quantity. So in the second quantity is the induced norm of the Hessian. So in this case, it's a bit less trivial to see how you can bound it. Does anyone have any idea how to obtain this transition? How can you calculate the Hessian of the logits with respect to the parameters of the model? It's a bit tedious, this whole argument, which is why I don't go too much into details, but I do want to give you a taste of what type of arguments are being used. So how can we estimate this induced norm of this quantity? No one knows. No one knows. Phi is WIBI. Yes. So basically, if you think about the parameters of the model for the network that we have, the parameters are just the concatenation of all the AI, WI, and BI, right? And if you think about it a bit more, notice that the summation implies that this second derivative of the logits with respect to the parameters is going to be a block diagonal matrix, if you think about it long enough. And so this quantity is just a block diagonal matrix. Now, this is the induced norm. The induced norm of a block diagonal matrix is the maximally induced norm of a block. Do these words evoke any memories in your mind from previous courses? Or are these alien words to you? Okay, Tristan seems to know properties of block diagonal matrices. So that's why you get just the supremum of this quantity, which is just one of the blocks in this Haitian. Do you want me to draw a picture? I can draw a picture. This is a picture of a block diagonal matrix where you have here something like theta. Here you have theta. And each one of these blocks would correspond to one of the summands. So this would be I equal to 1 all the way to I equal to m. And because you have f equal to sum from I equal to 1 to m of a bunch of quantities, these quantities are non-interacting. And so that means that the second derivative is going to be a block diagonal matrix. And then if you look at the induced norm of this block diagonal matrix, again, it's going to be just the induced norm of a single one of these blocks. And that's why you have this induced norm of a G. You see here it says G. G is one of the elements in the summation. Okay, so it seems like Tristan believes. The rest seem less clear. Does anyone want to ask any questions? No questions. Okay. The point is that you can calculate this induced norm of this single block in just closed form, because it's essentially just the induced norm of a function g. It's just the Haitian of this function g. It's just something. It's just a constant of some sort times this alpha m. So this gives you an idea of what type of arguments go into calculating this upper bound. If you want to see the rest of the argumentation, you can either look at this slide more carefully or look in the paper. Okay, so the main theorem in this paper that we're discussing is that what they show is that the distance between the parameters at time t and the parameters at initialization, the L2 norm of the distance, if you take the supremum over all time steps, it behaves like O of 1 over alpha. In simple human words, what does this mean? In human words, explainable to a pedestrian in the streets of Toronto. Sorry, Toronto, that's how you pronounce it apparently, Toronto. It goes to 0, that is correct. As alpha gets big, that is correct. So as alpha gets big, the change in the parameters goes to 0, which implies that the parameters are not changing too much. And so that means that we are in a lazy regime. What does the second statement say? The second statement says that the distance between the parameters and the linearized parameters goes to 0 as alpha tends to infinity. So again, what does that mean? It means that your model is equivalent to a model that you would get from training a linearized model. Becomes more linear, as Neo put it succinctly. Did I pronounce it this time correctly? Okay, there's progress. Now, the last statement says that the distance between the predictions of regular and linearized model behaves like O of 1 over alpha squared. So if you remember, this is basically the predictions of a linearized model. So it's essentially the predictions of the NTK, whereas these are the predictions of a regularly trained network. And you can see how they align as we enter the lazy regime. Increasing the variance causes us to be in a linearized model. Okay. So here's again the picture. Hopefully now this picture makes a lot more sense. Large variance, lazy training, parameters don't move, basically NTK. Small variance, parameters move a lot, and we get something much more interesting. Okay. Okay. So these measurements show that if at this point I haven't really shown why would you want to be in this active regime versus the lazy regime. The fact that we use the pejorative word lazy does not imply that it's a bad regime to be in, right? The word lazy does not convey that it's a bad regime to be at. So this experiment shows the population loss as function of theta. So here we're being active and here we're being lazy. So you can see that if you're being lazy, your test loss is going to be large. If you're going to be active, your test loss is going to be small. So which one do you prefer to be, active or lazy? Active, that is correct. The left-hand side plot seems to be showing how does the test loss behave with increasing number of neurons, M. So, oh, Gina has a question.
Yeah, I guess for some reason, probably because I like linear systems, wouldn't we kind of want the system to kind of be linear? Wouldn't it make computations easier and things like that?
I don't see how it would make computations easier. Maybe you have some idea about how to make it simpler if it's linear that I'm not aware of. But I think what's, the underlying message here is that there's been a battle, a war for years between neural networks and kernel machines, right? It's kind of like a war that's been going for a long time in the machine learning community. And then these people come and say that neural networks are equivalent to kernel machines. So that's like literally blasphemy. You cannot do that. And so what this paper is saying is that there is actually no equivalence if you're in this active regime. I guess I didn't answer your question though. I think the answer to your question is that this paper indicates that if you're in a linearized regime, then your performance is going to suffer. And so you don't want to be there. And basically the reason why they don't want to be in a linearized regime, besides these generalization properties, is that in a linearized regime, you're essentially not doing any feature engineering. Like your prediction is your optimization is not learning anything, right? Like if you look at this plot, in the lazy training regime, you don't actually find what are the underlying God-given directions, right? You don't converge to neurons which sit on these three important directions, right? So it means that your training is not doing anything. There is no feature engineering.
But then why would we linearize in the first place if we knew?
So we don't linearize. What happened was that there was a paper, which is the NTK paper, and that paper claimed that deep networks are operating in a linearized regime, right? And so these people came and said, no, they're not operating in a linearized regime. They operate in a linearized regime only if you initialize them incorrectly. But no one initialized like that networks in the first place. Like if you talk to a person, who's working on this deep learning in practice, like for applications, no one is initializing in a manner that would force kappa to be significantly less than 1. Does that make sense? Any other questions?
How do we reconcile that though with the theorems about convergence to the NTK? Because there was no restrictions on the.
Because if you look carefully at the paper of the NTK, the theorems are assuming that the variance of the weights is initialized with 1 over square root of the width.
I see.
And that is conducive of laziness.
And what should be done? Is it 1 over n?
1 over NL. By the way, if you think about it, it's very, very clear that one should do 1 over NL. Like if I show this to a person on the street, right, and ask them what should alpha m be equal to, obviously the person would say 1 over m, right? Because this a sum multiplied by a constant. What should be the constant? 1 over the sum, the elements in the sum. right? So the NTK bent the rules by using a different non-intuitive scaling that resulted in laziness. Reza is saying, as I recall, it's the first time in this course that initialization has such a great role in general dynamics of neural networks. Is that correct? That is correct. That is correct, Reza. That is correct.
So I was wondering, so does this mean that in the case where you use this 1 over square root n initialization, you still have this convergence, but it's converging to some, and you can still achieve 0 training error, right?
Yeah.
But this is a minimum. This is a neural net which doesn't generalize well, whereas you need active training. You want active training to generalize well. Is that the claim, or?
I believe the claim is that it generalizes worse. It can still generalize well.
Okay, I see what you mean. It generalizes worse. Okay, and so follow-up question. So they made some claims about the fact that this only really has to do with the scaling and not the overparameterization, right? Mm-hmm. So is there still some, like, what are they saying that like this significant overparameterization is not important anymore? It's not so critical, or?
Well, luckily to us, Neo will actually answer your question in his presentation, I believe. So the role of overparameterization is actually to make the optimization feasible in the first place. If you don't have overparameterization, you won't even get to zero loss.
Yes. Okay. Yeah, that was my thinking as well. Okay. But I've also seen in those papers where they're talking about overparameterization, they say overparameterization allows you to, essentially have lazy training. Like you don't have to search as far, and that makes SGD easier, right? Because you don't have to go as far to find a.
So that's not correct, because that's not correct, because you can see it very clearly in this experiment, right? This experiment shows that your neurons do find the chosen directions. Mm-hmm. God is my way of saying a teacher, by the way. In case you don't like the word God, I don't want to impose religion on you. Okay. I think you're not muted, Justin, by the way. Okay, so this paper does experiments where they try to understand how it's basically answering Justin's question more in detail. So Justin asked, how good is the performance of a lazy trained network versus an actively trained network? So here you can see again on the left-hand side, lazy versus active, right? And you can see how for an actively trained network, you get good test accuracy, roughly 90%, whereas for a lazy network, you get pretty bad performance. And this is the accuracy on CIFAR-10. So in CIFAR-10, if you just guess randomly the label, you would get 10%, right? It's very hard to get less than 10%. But so lazy training still gets above 10%. So it's not like it's doing something silly. It's just not as good. On the right-hand side, you can see, let's see what's interesting here. So you have ResNet, or let's say VGG linearized. Y just means that it's the number of channels was multiplied by a certain number. So you can see that VGG, if it's linearized, achieves 61.7% test accuracy versus standard training of VGG, which achieves 89.7. Here, the discrepancy seems huge. I would caution about, I don't want to question their experiments, but I would say that other papers show that the difference between linearization and standard training is not as significantly large. So I would suggest you to take this with a little bit grain of salt. Okay, so what is the summary of this lecture? The summary is that there's two regimes, lazy training and active training. In lazy training, the nonlinear model behaves like a linear model. And it occurs if you have a large initialization, and it's basically equivalent to the neural tangent kernel. Whereas in active training, you have a nonlinear dynamic, and it occurs if you have small initializations. It seems to perform better than lazy training, and it seems to be the regime in which modern deep learning is operating. Okay. With this, we are ready to proceed to our next topic. So the next topic is going to go back to the ideas of what exactly are we converging to if we're in an active regime. So if you have, let's say, a two-layer network, which is of infinite width, what is the network going to converge to if it's not being lazy? Because we know if it's not being lazy, the parameters are moving around, right? Converging to something interesting. What is it going to converge to is the question. And so what we're going to do is we're going to discuss again. So we're going to try and connect the ideas that were presented in the course. So we talked about the max margin classifier, we talked about neural collapse, and we talked about the neural tangent kernel, right? So if this lecture is about active learning, it means that it's not about the neural tangent kernel, right? So this is not relevant. And the question is, how is neural collapse and max margin related to this active regime? Is that a valid question in your opinion to be asking? It is a valid question. So the idea is as follows. If you have a two-layer infinite width neural network, and if you're operating in a regime where alpha of m is equal to 1 over m, so you're active, then what is your classifier or network going to converge to with your active training? Does anyone have any guesses? What are we going to converge to? Neural collapse. That's an interesting hypothesis. We shall see if that's correct. So neural collapse is one possibility. I guess the fact that there's a lack of neural collapse in the slides, it's betraying the hypothesis. So the other thing you might consider is max margin, since it's appearing here. Yeah, thank you, Neo. Thank you. And we'll see why is there max margin or why is there neural collapse. So what we're going to do is discuss this paper. We're almost running out of time. Let's just read the abstract. You know, I like reading the abstract because then you can kind of see how your knowledge is progressing. Before the course, probably if you read the abstract, you don't understand what these words mean. Hopefully now you understand most of these words. So the paper is called The Implicit Bias of Gradient Descent for Wide Two-Layer Neural Networks Trained with the Logistic Laws. So here we can see a comeback of the idea of implicit bias. So implicit bias, I remind you, means that you're doing optimization and your solution tends to a special category of solutions that a priori you might not expect to see. And gradient descent, you hopefully understand what that means. Wide two-layer neural networks means that it's the model we were just discussing in the lecture. And logistic loss is the same loss that we're discussing in the max margin lecture. So the abstract says, neural networks trained to minimize the logistic, aka cross entropy loss with gradient-based methods are observed to perform well in many supervised classification tasks. Towards understanding this phenomenon, we analyze the training and generalization behavior of infinitely wide two-layer networks with homogeneous activations. So at this point, you know what homogeneous is. You know what an infinitely wide two-layer network is. We show that the limits of gradient flow means that we're taking step size tending to 0. On exponentially tailed losses, just forget about the words tailed and just think about it as an exponential loss, can be fully characterized as a max margin classifier. We've seen these words in the past, max margin, in a certain non-Hilbertian space of functions. In presence of hidden low-dimensional structures, the resulting margin is independent of the ambient dimension, which leads to strong generalization bounds. In contrast, training only the output layer implicitly solves a kernel support vector machine, which a priori does not enjoy such adaptivity. Our analysis of training is non-quadratic. Okay, let's stop reading. So basically, what they're saying is that if you have an infinitely wide neural network and you do gradient flow, you will converge to a max margin solution, right? So the question of whether there's going to be neural collapse is still up in the air, still unclear. So it seems like we have only 2 minutes left in the lecture, so I will not proceed. And we will end here and stay for questions. Thank you for joining and see you on Thursday.
Can I ask a question?
Yes.
Does this mean that this whole thing about the unrealistic initialization that you need for NTK, does that mean that we should ignore, like, is there still value in NDK in some way, or is it just an unrealistic thing that we should be ignored?
I think if you look at some experiments that people do, it seems like the difference between the performance of NTK and the active regime is not as extremely large as one might think. So that seems to indicate that the fact that neural networks can sometimes operate in a kernel regime is very interesting because of this battle of kernels versus neural networks that has been happening for like, I don't know how many years at this point, like decades.
Yeah.
I don't see, oh, sorry, go ahead.
I just was going to say, I saw Francis Bach once tweeted that 2021 will be the year of the kernel, something like that. So he's,
oh, yeah?
Yeah.
But he's writing paper that disproved the fact that
I know.
It's a bit confusing of a statement.
It is confusing. Anyway.
I think that the main issue, personally, from my point of view, the issue with kernels is that they simply don't scale. Like empirically, if you open a startup tomorrow, right? You open a startup for predicting stock exchange and you go and, now the stocks are high dimensional data. You have a bunch of data, a bunch of training points. So kernel methods don't seem to be scaling well once your sample size is very large. As far as I'm aware, no one ever solved that issue. And neural nets are very, very efficient, extremely efficient. And that's kind of my point of view on that it's just way more efficient to train a network.